Hey, good afternoon, everybody. This is session 5BC of the GSE UK November conference. Steve Warren's going to be taking us through protecting data through encryption of coupling facility structures. Please feel free to post your questions in the chat and Steve will respond to them as we go. With that, over to you, Steve.
Hi, and welcome to Protecting Data Through Encryption of Coupling Facility Structures. My name is Steve Warren. I work at IBM in Poughkeepsie, New York in the United States in the IBM Garage for Systems, where I am an IBM Z technology architect. My role there is to help clients embrace the very latest in IBM Z technology. Today we're going to be focusing on learning about one major aspect of pervasive encryption. That is to encrypt your coupling facility structures. So join us in the next hour as we take an in-depth look at what it takes to encrypt your structures residing in the coupling facility. We've seen it all over the news. Data breaches are an increasingly growing concern to the corporate world. These breaches are costly on a number of fronts, including the cost of a breach to repair the data and to remediate the loss, and the cost in loss of reputation to that organization. We've also seen the vast majority of these data breaches get access to data that was totally in the clear and not encrypted. In a well-planned defense in-depth strategy, encryption of data is one of the key mechanisms to prevent a malicious bad actor from obtaining access to our critical data. With the increase in breaches comes increased regulation by many of the regulatory bodies around the world. The European GDPR regulation is just one of many that seeks to enforce the protection of a client's data. And there are fines that can be really high. These are direct quotes from the GDPR standard, maybe up to $20 million, 20 million euros, or 4% of the company's global annual turnover from the previous financial year. That's an incredible amount of money. And of course, we have to notify all of the folks that we have had a breach. And this is not only costly to notify the folks, but it also is damaging to your reputation. But look at this last sentence when it talks about notification on this screen. If prior to the breach taking place, the data were rendered unintelligible, i.e. encrypted, businesses will not have to notify the data subjects of the breach. So as you can see, while there are very strict rules and regulations around the protection of the data, if the data was encrypted, a lot of the requirements for GDPR can be waived. So as you can see, encryption is a very important part of a defense in-depth strategy for an organization. IBM has published many cost of data breach reports over the last number of years. And in that, they try to provide some numerical data supporting how expensive it is for a data breach to occur at a particular organization. So in the United States, the average cost of a data breach is $3.86 million. And there are some mitigating factors, however, that can actually reduce that mitigation. And one of them is extensive encryption. And on average, they found out that by doing extensive encryption, that the cost of a data breach could be incredibly reduced by having all of my data encrypted. And some of the other factors which can actually cost money, and other factors which can reduce money. So as you can see, encryption of data is a very important aspect of your total defense in-depth strategy. And so we're going to be focusing a little bit more about encryption. So let's say now we have come to the conclusion that encrypting our data is incredibly important. But how do we accomplish that? Isn't that going to involve a tremendous amount of cost to our organization, both in terms of having to modify our applications to actually take advantage of this encryption, and isn't that going to be very expensive because encryption of data and decrypting of data takes CPU cycles, and we need to meet our SLA agreements. Well, that was in the past prior to the introduction of the Z14 and Z15. And so with the Z14 and Z15, we can encrypt all of our application data without making application changes and no impacts to SLAs. And this would be part of a defense-in-depth encryption strategy for a multi-layered threat defense. So the idea is, with the Z14 and Z15, we don't have to make application changes, and it runs so fast that the impacts to our SLAs are very minimal. And so now, with this new hardware in place, we can really leverage encryption in a very cost-effective manner. Let's take a quick look at the data protection timeline on the IBM Z. So back before the start of the new millennium, IBM integrated the crypto hardware directly into the box, again, improving transaction throughput and allowing encryption activities to not always be using general purpose processors. In 2006, we also encrypted storage, self-encrypting tape and disk drives. This allowed you to have the entire disk or tape drive encrypted, such that if it's taken offline, the data is rendered useless to an outsider. What we're talking about and focusing on today, however, is this middle area, pervasive encryption. And pervasive encryption is talking about 100% protection of Z data within the system. And there's a number of aspects of pervasive encryption we'll talk about just briefly. There are a couple other things that have been introduced more recently, such as fiber channel endpoint security, again, ensuring data integrity on the hardware level, HyperProtect data controller, data-centric protection on or off the IBM Z platform, and then data privacy for diagnostics. So you're able to take a dump and to be able to ensure that PI protected information and data is not available for the first person debugging a problem on the system. So there are many things that make up a complete pervasive encryption solution. And so we're going to just be focusing on one of these today, which is the coupling facility. But there are other things we should talk about too. Let's start at the top. We already talked about full disk encryption and integrated crypto hardware. Those are key components that need to be part of a pervasive encryption solution. And in particular, the integrated crypto hardware on the Z14 and Z15 is substantially faster than on prior generations of hardware, right? Making encryption within the realm of possibility for almost everyone and to meet their SLAs in a timely manner. There's the aspects of networking. How do we identify and potentially restrict unprotected traffic coming in and out of our mainframe box? We also have talking about data set and files encryption, and when we're talking about the ZOS aspects of that, we can control just about any data set type now, and to be able to transparently encrypt that data to applications and provide separation such that different folks have access to different amounts of data, and the fact that the data administrators, while they can administer the data sets, they can't have actual access to the data itself. And then we're going to drop down to key management. Of course, with any encryption solution, the linchpin and the key strategy that you need to be thinking of when you're starting an encryption solution is, how do I manage the keys that are protecting these encryption activities? Without a good key management, you might as well just throw the data away, because if you lose one of those keys, the data is rendered useless. And so this is very much an important aspect of the pervasive encryption and complete solution. And then, of course, there's this middle thing, protecting the ZOS coupling facility data end-to-end using encryption that, again, is transparent to middleware and applications. So let's drill into that aspect for the rest of this talk today. So what we're talking about here is the encryption of structured data stored in the coupling facility. First of all, many folks may ask, do I really need to protect the movement of data from one part of my data center to another? In other words, my CPC to an external coupling facility just a few feet away? Well, maybe. We know that in a zero trust approach, we aim to wrap security around every user, around every device, around every connection, every time. And why? Because with this approach, we want to give the least amount of access possible to individuals, whether they're inside or outside our organization, to mitigate both outside and insider threats. Even if you're not really ready to embrace a zero trust approach, what about if your coupling facility links leave the bounds of your data center? That data is running in the clear in a non-controlled environment and could be susceptible to bad actors. Also, what about this scenario? What about your audit and compliance folks? Will your auditors require that any data leaving the mainframe for any reason whatsoever, that it needs to be encrypted? These are some of the key points when to decide when to encrypt your CF structured data. Well, let's talk a little bit more about the technology itself. CF encryption aims to encrypt all data in the coupling facility that could contain sensitive data. It does so using the very fast CPAC-F on-chip encryption technology on the host before even going over the coupling links. So what this means is that both the communication paths from the host to the CF, as well as back to the host, are encrypted. And of course, the CF structures at rest inside of the coupling facility are also encrypted. The data is only decrypted when it's back inside the host, right? Note that also that, like data set encryption, coupling facility encryption requires no application enablement or changes. In other words, a configuration change is all you need to do. Lastly, note that list and cache structures are supported while lock structures are not, and this is for a good reason. List and cache structures are where potential sensitive data could be stored. So many folks are familiar with dataset encryption, but not necessarily familiar with coupling facility encryption. And the purpose of these two slides, this slide and the subsequent slide, are to show that the processes and the things that you need to do to enable encryption, whether it's dataset encryption or CF encryption, are remarkably similar. In fact, they are the same 4 steps. Both need to create the encryption keys, define a policy that will indicate what needs to be encrypted, activate the policy so that the system can apply the desired rules, and then do the necessary data encryption. So really, at a high level, the two processes are remarkably similar. If you've already started down the road of dataset encryption, enabling encryption of CF structured data doesn't really require any new processes or skills. It's the standard procedure used to make policy changes. We just need to make use of this new encrypt keyword when defining the structure. If you have not gone down the dataset encryption road and you wish to enable CF structure encryption, there's going to be some additional steps that you're going to need to follow in terms of your key management of your master keys and some other miscellaneous items that you need to have in place prior to doing encryption of data on ZOS. Let's just go through these 4 steps and have a high overview of what things we need to do in order to enable CF encryption for a particular structure. The first thing is we're going to go into our CFRM policy input. This is usually a job, IXC-MIAPU, the XCF coupled dataset utility. And we're going to find our CFRM policy, and we're going to, for every structure that we want to encrypt, we're going to specify a new keyword called encrypt, and you're going to give it the qualification of yes. For any structure we do not wish to encrypt, we can either say encrypt no or don't specify anything, because the default is encrypt no. Once we decide on which structures we want to encrypt, we're then going to submit this job. And what this is going to do is it is going to add or replace the new policy. And XCF, for every structure that you've identified encrypt yes, is going to go out to ICSF and ask to create a new encryption key and to wrapper that key, and we'll talk more about how those keys are protected in the CFRM CDS. So notice all these structure keys are stored in the CFRM CDS. Okay, that's great. We have keys in there, but we don't really know that we want to actually encrypt the data until we actually start that policy. And so the XCF command, this XCF start policy command is going to activate the policy. This is business as usual whenever we make a change to our CFRM definitions, for example, in the couple data set. To activate it, we have to issue this command. So now we have one or more structures that have a designation of, these structures need to be encrypted. However, you might have already used those structures before, and the data out in those structures is unencrypted. And we can't have a mix of unencrypted and encrypted data. And so what's going to happen is this structure will go into something called a pending state. And the pending state will be resolved whenever you do a rebuild of that structure. And of course, you can just use the reallocate command to be able to complete this rebuild activity. So what will happen in that case is that the existing data for that particular structure will be read into the system. It will be encrypted using those keys that we created in step 2, and then it will be sent back out to the reallocated structure. All right, that was a high-level overview, but there's a lot more that we're going to talk about now into some of the details related to CF structure encryption. So hold on to your seats. We're going to take a dive into a little more of the innards of CF structure encryption. So this slide here kind of summarizes some of the things I talked about just on the previous slides, and talks about some of the little more higher level concepts in words. Let's go through this one by one. The first thing that we need to do is that we need to understand of this encrypt yes and encrypt no keywords. We've talked about that already. If you say encrypt no or you don't specify it at all, the structure will not be encrypted. If you say encrypt yes, that signals XES that it needs to encrypt this data. The CFRM does much of the key management. So this is an important fact to understand as well. The XCF coupled dataset utility, policy utility, is going to use ICSF services to generate the structure encryption keys per encrypt keyword. So you're going to have a unique key for every single structure that you have that you've specified encrypt yes for. Now what's nice is that this supports dynamic changes to these structure encryption keys, as well as the master AES key, which may be updated unbeknownst to our sysplex sysprog. Notice also that the CFRM coupled dataset is the key store. This departs from probably where most keys that are created by ICSF are stored. They're usually stored in something called the CKDS file. In the case of XCF and CF structure encryption, this is stored in the CFRM couple dataset. This is for a number of reasons, one of them being that this structure needs to be shared amongst every member of the sysplex, and we know that the CFRM coupled dataset is a dataset that is shared with all the members. The next thing we need to understand, and kind of again a refresher of what we just talked about before, is that the encryption and decryption is host-based, meaning that ZOS does it. The exploiters are neither aware of nor involved in the encryption. And as well as the CF and the CF links, they're not involved, they are unaware that the data is encrypted either. Now, of course, the exploiters can find out if the structure is encrypted if they so choose. In other words, it's transparent, but it's not completely invisible. I don't know if many applications would really even care. So the bottom line is, if you don't look for it, you will never even know that the data is actually encrypted. And then a couple other points here. Changes to the encryption state of an allocated structure occur dynamically through structure rebuild processing. So we'll have some slides right after this that will explain that in a little more detail. And so the last point we'll make here is that all entry and adjunct data flowing between the ZOS and the coupling facility is encrypted. So the intent of dataset encryption is to encrypt data that might reasonably have sensitive data. Control information and related metadata is not encrypted. So the only time that might be of concern to you is if your control data, for some reason, contains sensitive data. So I don't know if you use some kind of key and that key contains sensitive data, which I would think that most folks would never do. That might be the only case where CF structure encryption might not capture and encrypt all of your sensitive data. But the intent is that entry and adjunct data are where the sensitive data really resides. And so all of that data is fully encrypted. So let's talk a little bit more about structure encryption keys. But before we do that, let's first talk about the concept of active versus administrative policies. For any couple data set, and here we're talking about the CFRM couple data set, there's the idea of an active policy, the policy that's in effect in this case for the coupling facility, and a set of standby policies known as administrative policies. So I can have an active configuration. I can also have another one or more other policy definitions defined that maybe have a slightly different configuration. And those things are kind of on standby. At any time, I can suddenly activate that policy instead of the active policy that's currently in play. And that will change the CFRM policy. So I can have, again, one active policy and more than one administrative policy. Okay, so now let's talk about structure encryption keys. First of all, every structure has a unique key. So that key is generated for a given structure when the CFRM coupled dataset transitions from no policy specifies encrypt yes for a given structure to at least one policy specifies encrypt yes. So whether that's the administrative or the active policy, if at least one policy specifies encrypt yes, when you had none and now suddenly you have one or more, that's the moment when that CFRM policy is going to cause the key to be generated. Those keys are, again, generated by ICSF. I'll get the acronyms right eventually. That key is generated by ICSF, and it is stored in the couple data set of the CFRM. And make a note here, the structure key itself is encrypted by the master AES key. So what we're trying to do with this color coding is to show the following. So let's say I have 4 structures in here that all of them I want to be encrypted. Notice that they all have 4 unique colors. The keys are all different for the 4 different structures. However, all 4 of those structures are wrapped with the same master AES key. So when you see the key itself is just a circle, but the secure key, as we refer to it, is the key that is encrypted by the master AES key. So why this second level of encryption? Well, that means that we can store this key in a data set of which we might have a lot of people having access to, but that key is completely useless to them because they can't use that key to actually decrypt the data. That is a secure key, which means that they first have to unwrap that secure key with the master AES key in order to get access to the key that is actually going to be used to encrypt the data. So that is very interesting. Another point that we should make is that that key is going to persist so long as there is at least one policy in the CFRM couple data set that specifies encrypt yes. So that key is not going to disappear from the coupling facility until there are no more policies that specify encrypt yes for that particular structure. And notice that the key will finally disappear when the CFRM couple data set does not have any policy specifying encrypt yes for that structure. So again, we're referring to both the active and administrative policies. As long as one of them has encrypt yes, we're going to keep the key for that given structure in the couple data set. On this slide, what we're trying to convey is that physically there can be multiple copies of the same secure key within a single CFRM couple data set. As we mentioned before, there's only one active policy, but there can be several other administrative policies that are kind of like standby policies that allow a installation to change the CF configuration in a very rapid manner by just having one of these standby policies go into effect. So for every instance of for a given structure, every time encrypt yes is specified for the structure, for the same structure name in this example, we're going to have a copy of that key associated with that particular policy definition. So for example, in the active policy, I have str4 and I said encrypt yes. So in that case, there's going to be a key there. There's also going to be a key stored for all the other policies as well. Now, from a usage perspective, you don't really need to worry about that. But from an actual storage perspective, to help you understand some of the concepts of what's going on here, I've included that piece of information here for you, that there, in theory, there can be multiple copies of the same secure key that are for the same structure if that structure has specified encrypt yes in one or more policies. This slide depicts the scenario that most clients will be starting out in. They don't have encrypted data, and now they want to encrypt data in the coupling facility. So, as we learned from step 4 a few slides back, the last step we need to do to read the data, to actually encrypt the data, is to rebuild the structure. So let's go through this in a little more detail. So let's say in the upper right-hand corner we have an existing structure with data in the clear. We don't just want to start encrypting the data. If we did that and we did not encrypt all of the data, that would give us a mix of data. There would be some that's in the clear, prior to us changing the encryption designation of the structure, and some that's encrypted from this point forward. Having mixed data of some encrypted and some not encrypted would be almost impossible to manage, let alone a more difficult proposition to convince auditors of compliance. So what we want to do is say either all the data is encrypted or none of the data is encrypted. And the way we accomplish that is through some kind of rebuild action, and for example, a reallocate. So what we're going to do is we're going to read that data, the unencrypted, the data in the clear, into ZOS. ZOS is then going to use a key to actually use the structure key to actually encrypt that data that was out in the coupling facility, and then write the data over the coupling links. It's already encrypted as it leaves the house and goes to the coupling facility, and it is stored encrypted. From time to time, due to regulations, procedures, audit requirements, it will be necessary, likely, to change the structure key. We're going to show you how you actually do that in just a few moments. But again, how do we actually use this different key? Well, again, we're going to read the data using the old key. We're then going to have the new key that we then can encrypt the new data and then push the data out. Now that data is encrypted with the new key. So even when we do a key change for a given structure, we're going to still use the same rebuild process to re-encrypt the encrypted structure. The reverse is also true. If we have a structure that already is encrypted and we decide we don't want to encrypt it anymore, we've transitioned from encryption to encrypt yes to encrypt no. What we can do now is we can simply do a structure rebuild to actually read the encrypted data in, unencrypt it, and then write the data back to the coupling facility. So just a little more details on the need to use rebuild in order to transition from encrypt to decrypt. Since the existing structure has to be rebuilt in order to accomplish any dynamic changes to its encryption state, the exploiter must support some form of rebuild processing. Okay, and we'll talk about system or user managed, right? So what we're saying is the following. If you have a brand new structure, of course, and you're encrypting it from the start, a rebuild's not going to be needed for that, for obvious reasons, right? So if I already am creating it for the very first time, it's not out there right now, I say encrypt yes, I don't need to do rebuild. I'm going to be able to start writing to it right away. But once the structure has been allocated, now I'm going to need to rebuild it to be able to make dynamic encryption related changes, right? I can make very disruptive changes if I want to by deallocating and reallocating the structure. When I reallocate it, it's going to allocate it encrypted, but meanwhile that structure has not been available for a duration of time between the time the deallocate is occurring and the time that I've fully reallocated the structure. So of course a rebuild is going to make a lot more sense. Now for duplex structures, you have to be aware, for system managed structures, of course, both of the instances are going to have the same encryption state. So they're either going to be both encrypted or they're going to be both unencrypted, right? If it's user managed, we have to be a little more careful. So you could have neither one of them encrypted. You could have both of them encrypted, or you could have one encrypted and the other not, and that is bad. Just imagine that you have one encrypted and the other not. You could run into a world of hurt in recovery scenarios, and so you don't want to avoid that. You want to avoid that, and so there is a health check that will complain if both duplexed structures are not in the same encryption state, and so you're going to want to make sure that you have that enabled, especially if you're doing user managed rebuilds. So let's just take a step back and look at the big picture of what's going on under the covers here. This is a great picture and I love it, but I can't take credit for it. Thanks to Mark Brooks from ZOS Sysplex Development for creating this. All right, so let's just take a moment and look at all the various pieces that are here. So we've already talked a little bit about the fact that these secure keys are created inside of the CFRM couple data set. And remember, that is done via this IXC MIAPU utility. So that in utility, when you specify encrypt yes, it for the very first time for a given structure is going to cause it to invoke ICSF services to generate what's called a secure key. He goes and gets that secure key from the crypto card. A unique key is generated and it is wrapped in the master AES key. Because it's wrapped in the master AES key that is used to encrypt and decrypt the data is not in the clear. In fact, it's very much unusable. And so we can with great confidence store that in the CFRM couple data set. Okay, so now we have these unique keys for different structures that are all wrappered with the same master AES key. Okay, so now what happens now when we're ready to actually use the structure that is encrypted? Well, the first connector that connects to a given structure in the CF that has the encrypt, that has a secure key already defined, what's going to happen is XCS is going to read that key from the CFRM couple data set, that secure key, and it's going to ask through ICSF, hey ICSF, can you go out and please convert that secure key into what's called a protected key. A protected key is what is going to be used when we actually are going to encrypt and decrypt the data. Now, why we're using a protected key? Well, first of all, this protected key is going to be stored in memory on ZOS, okay? And we're going to have this in memory. We're not going to go out to the data set every time. The second thing is this protected key is encrypted by what's referred to as the LPAR key. There's a unique LPAR key for every single LPAR, and every single time you IPL the LPAR, you also will get a unique key. This LPAR key is wrapping the structure key that we have here. And so CPAC-F, which is a very fast, it's the central processor assist for cryptographic functions, is a very fast cryptography functionality that we're going to be using. It's right on the processor itself and allows us to run the absolute fastest cryptographic functions. And so CPAC-F takes as its input a protected key, which means that the key is wrapped in what's called the LPAR key. So imagine, so the first time I connect to a CF, if it's a encrypted structure, XCS is going to go out, grab the key. It's going to ask, can you please convert this into a protected key? So on the hardware itself, it's going to take the master AES key off, and it's going to put instead the LPAR key in it. Now, this LPAR key is only available to the hardware. It's not available to software. So again, at any time, we do not have the key in the clear. And the only way that key, that our protected key can actually have this protected key wrapper removed, the LPAR key removed from our key, is when we call CPAC-F. We call CPAC-F, passing the data, and it goes, removes the LPAR key, and then uses the key that we have inside to actually encrypt the data. Okay? So that's the process of how things work. Now, of course, there are lots of things that we need to be considerate of. One thing is, what happens, can we change these keys? We're going to show you how you can actually change the keys for a given structure. What happens if the master key, the master AES key is changed? How does that affect everything? We're going to go through detail for that. What about a system IPL? Well, system IPL is going to change this LPAR key, and a new protected key will be generated from the secure key. Not a problem. We'll talk about some disaster recovery, Sysplex IPL, and stale couple data set issues as well. And we will also deal with the fact that not all of the data is actually all the couple data sets may be online. There may be some offline couple data sets. We need to make sure that when we take an action, that those offline couple data sets that we may need for disaster recovery or other backup purposes, that they will be up to date with the CF encryption picture. So stay tuned for a whole lot more about some of the pieces of this puzzle. So let's just reiterate again how encryption actually works now. So when we actually are ready to encrypt the data, here's what happens. Each system within your sysplex is going to fetch that same secure key from the CFRM couple data set when connecting to an encrypted structure. That secure key is then going to be converted into an LPAR specific protected key, which is actually going to be used for the actual encryption and decryption. So once I have the secure key, I'm going to then convert that into a protected key and store that protected key in memory. That protected key is useless without calling CPACF, right? So now we're going to actually, we have the user data in the clear. We want to actually have an encrypted copy of that user data. We're going to call the CPACF function copy and encrypt, specifying that protected key in the data. The data will be encrypted. We then flow it over the coupling links to the coupling facility and store it in the structure. Likewise, when we're coming back and we'll read the encrypted data, we have that inside an XCS buffer. We'll then call the CPACF function decrypt and copy using the protected key that we have in memory. The CPACF will then take that data and will then unencrypt the data, and the user data will be in the clear again. So remember, the CF and the CF links have absolutely nothing to do with the encryption or decryption. Okay? We're going to talk in just a moment about SMF metrics, but through the ZBNA utility, we're able to estimate or measure the cost of copying and encrypting the data. And so this is a great planning tool that you can use to have a better idea of how much this is going to cost in terms of speed to copy the data, to encrypt the data. Just to reiterate the point that we encrypt entries and adjunct data, we don't encrypt controls and metadata. And because lock structures are just controls and metadata, we don't do lock structures at all, right? So we're talking about list and cache structures, right? So in the case of list and cache structures, of course, we don't know or understand the content of the entries and the adjunct data. It may or may not be customer sensitive data. So to that end, those are the things that are going to be encrypted. If you have sensitive data inside of those lists, inside of the entries, for example, that you need to sort on, and now that it's encrypted, it will not be sorted in the coupling facility the way you wanted, then you might have to, consider what application changes might be necessary. But in general, for most folks, we have experienced and we anticipate for the majority of folks that no changes will be needed to exploit coupling facility encryption. So like we said before, that the master AES key is used to wrapper the keys that are stored inside the CFRM couple data set. We call those secure keys, right? Now, from time to time, you will have the master key, the master AES key, changed. And when you do that, there is a facility that will cause an ENF signal to be sent to all of the exploiters that have registered for that. And basically what happens is they're going to say, in this case, hey, XCS, the master AES key has changed. XCS is going to see that change, and it's going to go out and re-wrapper all of the keys automatically. And that will be for all the online CFRM couple data sets. If you have a offline couple data set, you're going to have to manually run the XCF couple data set utility for couple data set policy utility to actually manually update those keys with the new master AES key. Okay, not a big deal, but it still needs to be done, and so you're going to want to make sure that that is done. Now, that being said, there's no impact to existing encryption work because you're not using the secure key to begin with when you are encrypting data. You're using the protected key, and that protected key, remember, was generated from a secure key. So once I have the protected key, as long as I'm IPL'd, I'm going to be using that protected key and until I have no more connectors to a particular structure, right? So the bottom line is that you have no impact to the ongoing encryption and decryption. So in words, let's just repeat some of the same things. So ICSF is going to notify all the systems of the sysplex of a change when the master AES key changes. In response to that, we're going to re-encrypt all the structure keys in the active CFRM couple data sets, both primary and alternate, with this new master key. Now, of course, the system is unaware of any other offline CFRM couple data sets that you might have, so you need to rerun the policy utility, replacing at least one policy that specifies encrypt yes. So when you actually make that call, you're going to be specifying the old secure key and the old secure key, and the crypto card does have a history and will be able to recognize that old key and will be able to then re-encrypt with the current key. But you want to, of course, make changes or propagate it too far because the crypto card only keeps so many copies of the master key, right? And again, changing the master key does not require data in the encrypted structure to be re-encrypted. Remember, we're only changing the wrapper of the key here. The key itself that's used to encrypt those structures has not changed in this case. So here's an example of messaging that occurs on the system when someone changes the master key. You'll see these things, these messages that appear: re-enciphering keys in the CFRM CDS, administrative keys have been updated, the active policy data has been updated. And so that is what you're going to see there for those messages. If you're running on a Z14, you're also going to see these additional messages. The bottom line is, once you see the change master key processing message at the bottom, it has completed successfully, it's now safe to request another master key change, right? And so again, this is what's done automatically to the active couple data sets. Okay, so we talked about changes to the master AES key. Let's talk about that structure encryption key, the key that actually is encrypting the data itself in the coupling facility. You may have rules in your installation that require encryption keys to be periodically modified. And so what we need to understand is the scope of the change that's required. We have to change all the keys in use, change all the keys that exist. So there's a number of different variable factors here. So there's three possible cases to really consider. When I want to update a key, does the key exist in the active policy? That's the first bullet. The second one is the key exists in the active coupled data set, but not in the active policy. So the key really is not being in use. And the last one is the key is somehow in an offline coupled data set. So if the key exists in the active policy, that was case number 1 before, it's very easy to generate a new structure key. You can simply do a set XCF modify str name equals the name of the structure, for example, or it could be a wildcard. You can have more than one thing, and then you say comma encrypt key. And what this is going to do, it's going to generate new keys and store them in the active policy, and then it's going to asynchronously propagate them to the administrative policies for that given set of structures that you specified on this setxcf modify command. So this is really cool. Now, of course, once you've done that, you have data out in the coupling facility, which has used that old key, and now you have a new key. So what you're going to need to do is you're going to need to issue a structure rebuild in order to actually make that coupling facility data to actually now be encrypted with the new key. Okay, so the first thing is issue the command and then do a structure rebuild for that particular structure. So here's how that would look when I want to change the encryption key for structure IXC1. I would specify this exact command, setxcf modify strname equals IXC1, comma, encrypt key. And you're going to see a flood of messages that come out. And then what you're waiting for is the fact that now that the encryption key is ready, the key change is pending for one structure. So what it means by pending, it means that I've updated the keys in the CFRM couple data set, but in order to take advantage of that particular thing, I need to do a structure rebuild. So a structure rebuild will now use that new key. It'll take the old key to decrypt the data and use the new key to re-encrypt the data. This diagram simply is talking about when I need to change the keys when the active policy does not specify encrypt yes for a given structure, but one or more of the administrative policies does make that specification. And on a couple slides from now, we're going to talk about the headaches you have to go through in order to get those administrative policies to update their keys in this scenario. Remember, if the structure is defined in the active policy, then all the structure definitions in both the active and the administrative policies will be updated by the setxcf command. But when there is no structure, when that structure does not have the encrypt yes specified in the active policy, this is where the headaches are going to come. In 2 slides, I'll explain a little bit more. The same goes for the IXC MIAPU if encrypt yes in an offline CFRM couple data set. You're going to also use the policy utility to generate new keys for all the structures yourself. So this is quite complicated. This is going back to that chart that we talked about just a few moments ago. The bottom line is, in order to do the scenario where I have a administrative policy that says encrypt yes, but I have the active policy where it says encrypt no, we told that you couldn't use the setxcf command to change those keys. But remember the rule that the utility is only going to generate an encryption key when a given structure has none of its policies defined with encrypt yes to having at least one of its policies defined with encrypt yes. So in order to induce the utility to generate the new keys, we have to do a very complicated procedure. And this is kind of, in my mind, this is almost a usability issue, that I either need to change all of the administrative policies to specify encrypt no for a given structure, and then change all the administrative policies back to encrypt yes. That will induce the utility to then to generate a new key. Or you could delete all the administrative policies that define that structure and add them all back. So it's not pretty, but it's what's necessary when the encrypted structure is not specified in the active policy, but it is in the administrative policy. Okay, so when you're running in the policy utility with encrypt yes, we need to, of course, run that on a system where ICF is started, because ICF services are used to generate the keys. Of course, we need access to use ICSF, so that job needs to have access to these particular resource profiles. And most importantly, the AES master key on the system where the job runs must be the same one used on the systems where the encrypted structures are to be used. So I can run the utility to actually generate the secure key that's stored in the CFRM couple data set on system A, but just remember that I need to use the same AES master key on systems B and C because it needs to be able to remove the wrapper, the AES master key wrapper, and generate the protected key, which uses the LPAR key in conjunction with the structure key. So this is a tricky one. All systems in the sysplex must have the same master AES key. Well, technically, if you are not doing a system managed rebuild, in theory, what you can do is you can get away with a subset of systems maybe having the same master AES key. It's highly recommended that you have all the systems in the sysplex use the same one. But in theory, all the systems that are connecting to a given encrypted structure have to have the same AES key loaded into their crypto express card, right? So that the secure keys from the CFRM can be conferred to the protected key that's going to be used to actually encrypt the data. If you're using System Managed Rebuild, I don't have enough time to really go over this in detail. Please read this and feel free to ask me any questions afterwards. Here's another caveat about be very aware with not having the same master AES key on all systems in the sysplex. I'm just going to let you read this at your own leisure. Likewise here, I'm going to have you read this material. The master AES key must be set before the system joins the sysplex. You don't want to run into this catch-22 situation. And so when you need to, this catch-22 situation is you need to IPL the system to set the master AES key, but the master AES key must already be set so XCS can use encrypted structures early in the IPL, et cetera, et cetera. And so the bottom line is the master AES key must be set before the system joins the sysplex. So this is kind of important. Encryption keys and offline CFRM coupled data set. For example, ones that use to bring up a sysplex and disaster recovery site. So again, the intention behind the spare offline CDS, as far as encryption keys at least go, is important. If you ever intend to use those coupled data sets in a new instance of the sysplex, for example, to bring up in a disaster recovery site, then you absolutely have to update the keys in the spare offline CDSs to have the master key that will be used in that sysplex. But the actual structure level keys in that data set will not be the same ones that will be used in the sysplex as in the active sysplex. As long as no structures survive the disaster recovery site, that's fine. So in other words, likely when I'm going to a disaster recovery site, I'm not going to have my structures survive. I'm going to build new structures. So it doesn't matter that I have different structure level keys for my remote disaster recovery site. Read this a little more. If you have any questions, feel free to contact me. So on the Z14 and Z15, we do an extra thing and a copy of the secure key is actually inside of the CF. What that means is that in the event that we lose the CFRM coupled data set, the system can recover and might be able to preserve the structure. So this is just an added enhancement for Z14 and higher. Let's quickly talk about some of the externals provided with coupling facility encryption. There are many ways to determine the encryption status of a structure. Some of them are display commands that are listed here. Some of them are ZOS health checks. There's the sysplex management plugin, RMF reports, and other programming interfaces. So here's an example of an unencrypted structure with encryption pending. So we've actually, this is the first time that this structure may have, been encrypted. And so when we're listing the status of the structure, it says pending policy information, encrypt equals yes. So in other words, in order to get out of pending state, we need to actually do a structure rebuild to put it into actual encrypted state. And as you can see, the active structure is not encrypted in this display example. Here's another display where we do this exact same thing, but now we've done the structure rebuild. So now it says encrypt is yes for the thing. And then for the active structure, it says even the encryption level, it's using the AES 256 protected key. And here's an example where I have a pending new key here. And so I've done the set XCF command to actually put to generate a new key, and it says yes, it's encrypted, but an encryption key change is pending, and again a rebuild will resolve that. The current structure is encrypted with protected key AES 256. Of course, there is a ZOSMF Sysplex management plugin that we've talked about in the Parallel Sysplex update, and in this case I can go down to a particular structure, and if I select that structure, you'll see in the subsequent slide what you're able to see. Here we're viewing properties for a given structure, and you notice that it has the little green icon. It says encryption status encrypted. In our RMF reports, there's a new column ENC, which also can say if it's encrypted or not. And this Monitor 3 CF report, real estate was really tight, and so the E column stands for encrypt. So in this case, we have a couple structures that have Y, so they are encrypted. The other structures are not. While CF structure encryption is supported on all of the latest servers that are available on IBM Z, you're going to get by far the greatest processor improvement when you're running on either a Z14 or a Z15, a much faster crypto card and a much faster CPAC-F card for encryption. So practically speaking, the Z14 and Z15 make the most sense to run CF encryption. From a software dependency standpoint, again, running ZOS 2.3 or higher is required for CF structure encryption. All systems must have the same master AES key. Just remember, if you have a mixed sysplex where you have a down-level system connecting to a structure, the structure can't be encrypted, otherwise it can't read it. And so in this case, it doesn't really matter because 2.2 is really out of service at this point. So in this case, 2.3 and higher can read the structure. And again, for software dependencies, you're going to need to make sure XCF and the utility have the necessary accesses to ICSF. Most of these migration and coexistence considerations don't really apply anymore since most people are now running at 2.3 or higher. And so just read through this. If you have any questions, contact me. Here's some service that might be of interest to you for different improvements related to CF structure encryption. So in a nutshell, with ZOS 2.3 or higher, you're now enabled to encrypt your structures on the CF. I'd like to thank you for joining me on this journey. Please, my email is on the title page. If you have any questions, please feel free to reach out to me. This session does go over a couple minutes, so I probably won't be able to take additional questions at this time, but I'd like to thank you, and please take a moment and fill out your session evaluation. You can scan the QR code or go to this website. Thanks a lot and have a great day.
Thank you very much, Steve. Another great presentation. Are there any questions from anyone?
Quiet group.
Yeah. Well, it's late in the day, I guess.
Yeah, it is.
So, to everyone, there's a few comments there. Loads to think about there. Thanks a million, Steve, from Eileen. It's saying, I understand that the encryption of CF structures protects the content of the structure. In example, a raw dump of coupling facility. Now, but if someone writes, I do not know if this is possible, a program to read, example, DB2 cache structure in a similar manner. DB2 does with the structure, the content of the structure the program can read. Are you checking this?
I'm reading it. So I'm not exactly sure the intent, but I'll make my interpretation of it. And then if it's not right, you can certainly either rephrase the question or get with me offline. So the way that we're doing this, we're doing it on a structure by structure basis, right? So we have structure A is encrypted. You're using XCS normal services to that particular structure, whether it's a cache structure or a list structure. You're using those IXL services to actually read and write unencrypted data out into the coupling facility encrypted. So XCS is the bridge to that encryption. So if you're writing a program that's issuing IXL services to an encrypted structure, when you come back, that data is going to come pre-presented back to your application as unencrypted for you to use. But the XCS is the bridge that is using that copy and protect function of the CPAC-F with that protected key to actually encrypt it out on the coupling facility. Does that make any sense? So you're always using XCS as the bridge. And so from your application perspective, you don't even know that it's encrypted or it's not, but it is. And XCS is bridging that gap for you. I hope that explained it a little bit. The coupling facility also has no clue that the data is encrypted. By the time it gets on the CF link going out to the coupling facility, it's already the data is already encrypted at that point. So the CF has nothing to do with that process. I don't know if that answered. Okay. Yes, I understand. Okay, that's good. Okay, good. That was a good question. Thanks for asking that. Anyone else with a question? It is a complicated topic, and there's a lot to digest there. And so maybe after the things process a little bit in your brain, you might have a question after the session. Well, again, I posted my email in the chat. It's also on the cover page of this slide deck. Feel free to reach out to me. We've had some folks, especially for the Sysplex update that we had before, we had several questions that came in, and we've been trying to, I tried to answer them as best as I could afterwards. So sometimes it just needs to settle in and for you to process a little bit. So I understand that.
Okay, I don't see any other questions. Steve, thank you very much once again. For everyone, our next session will be tomorrow, 12 p.m. UK time, and we will be talking about introducing REST-enabled BCPIs, a whole new way of controlling your Z hardware. Until then, have a great evening. Thank you.
All right, see you tomorrow at noon.
Cheers.
Bye-bye.